Good morning. Welcome to a new live stream. Welcome to a new office hour. I wonder, yesterday someone said the audio was better. Could just be the acoustics of this room. Could also be the fact I'm deliberately talking very quietly because I'm in a hotel. And it's 6:30 in the morning here. So I wonder if that's it. Maybe I just need to be less loud and the audio's better. I don't know. It's going to be a very short office hour again today. Because I'm still at a conference. And, yeah. I don't know if Fimnal's going to be in chat today. But it is on my mind that the other day they asked about the representations of SL2. And I kind of want to talk about that. Also, there was someone who asked about the Yoneda lemma like a week ago. I don't remember who it was, but they were asking for some more, I don't know, intuition for it, or why we would care. Yeah. So I guess that's what we'll dig into. I wonder if anyone's going to show up this extremely early office hour. Okay. So, well, which of those should I dive into? Let's talk about the representations of SL2. So let's look at the Lie algebra. SL2C. These are matrices whose trace is equal to 0. Well, and what's the Lie bracket on them? It's just the ordinary matrix Lie bracket. So xy minus yx. Well, we can write down a pretty explicit basis for this thing, right? Because it is, after all, a vector space. So it's all 2x2 traceless matrices. Well, the only way that this could have trace 0 is if the entries were A and minus A. So pretty clearly then, we have a basis as such. So normally we call this matrix H, we call this one E, and we call this one F. Hello, duck with a monocle. Glad to have you back. Glad to have you back. So, what Lie algebras can we... let's take a look at some representations first, and let's take a look at their behavior. So, what is a Lie algebra representation? Well, it's a Lie algebra homomorphism into the Lie algebra of some vector space, right? But the Lie algebra of a vector space, this is just, so if V is n-dimensional, this will just be GLN V. Well, of course, good morning, Dead Star. SLN naturally sits in, or I should have said GLC, right? SLN naturally includes here. So we could take the natural inclusion, right? In other words, we could view it as acting on the vector space C2, where each of our matrices just acts by ordinary matrix multiplication. So let's take a look at this vector space. In particular, one thing we could look at is, well, let's also work out our, maybe before we do that, let's also work out some of our Lie brackets, right? Because that's sort of the structure of our Lie algebra, right? It's a vector space with this bracket, and we have a basis. So if we knew exactly how each of those bases elements pairs under the Lie bracket, we could then use that to determine the Lie bracket between any two elements. So maybe that's useful to work out ahead of time. I mean, in fact, you can prove that that is sufficient to completely determine your Lie algebra. So we have, let's go E, no, let's go H first. So we can go H, E, that will be 1, 0, 0, minus 1, 0, 1, 0, 0, 0, 1, 0, 0, 1, 0, 0, minus 1. Multiplying through, we get 0, 1, 0, 0, minus 0, minus 1, 0, 0, which just becomes 2 times this matrix, which is 2E. Okay. Now we could look at HF, and, well, okay, let's just do it. You can probably guess it's going to be a very similar computation, right? Zero, 0. Now we'll get minus 1, 0, and 0, 0, 1, 0, and we get minus 2 times F. Now, remember that the Lie bracket is anti-symmetric, so we already know what E bracket H is. It's just going to be the negative of this. So the only one left to check, really, is just EF. And that will be 1, 0, 0, 0. And, oh, that was my alarm to wake up. Too quick. Oh, I did something silly. I wrote the matrices in the same order twice. It helps when you already know what the answer is supposed to be. This would be 0, 0, 0, 1. In other words, we get H. Okay. So we have our Lie brackets. HE is 2E. HF is 2F. And EF is H. So now we can work out, let's maybe try and work out what the, you know that matrix. Good. So how do I justify? I know the next step I want to do, but I'm trying to justify how I explain this as the right step. Why is the next step the right thing to think about? Hmm. Yeah, I don't know if I have a good explanation. But the next step is to find the h. Uh, the next step. I mean, there is a good explanation, but it's a higher level thing. Once I explain the thing that h generally belongs to. So and the next step is to find the eigenspace, the h eigenspace. This is that Lie algebra. Yes, indeed. Yes, indeed. It is the Lie algebra of SL2C. So let's suppose we've got some vector xy, and that multiplying by h has the effect of scalar multiplication. So we would get x and minus y. But of course we can see that in order for this to be a non-zero eigenvector, well, let's see, there's two possibilities, I suppose. So we have these two equations, lambda x equals x and lambda y equals minus y. So if x were non-zero, then lambda would have to be 1. So we have x non-zero, lambda would have to be 1. But we see from this equation that would force y to be equal to 0. So we have a 1 eigenvector being 1, 0. And then conversely, we could suppose that y was not equal to 0, in which case lambda would have to be minus 1. But then, of course, we can see that would force x to be 0. So this is we have a decomposition of sorts into a eigenspace, one eigenspace and a minus one eigenspace. And you might go, well, big whoop, I could have pulled that decomposition out of my butt. That's just the standard basis of the 2x2 things. Not surprising. And fair. But we're going to see what the other elements do to these eigenspaces. So if I take h, or if I take e, let's say e, and I act on this vector, well, that will just be the 0 vector. If I take e and I act on it, I act on the other vector, that will actually change eigenspaces. So I have this picture. So of course we have h acting on this eigenspace. We have e taking us between these two eigenspaces. It then kills this one. H acts on this eigenspace. And then finally, as you might imagine, a very similar but opposite story happens with f. So we get 0, 0. And we get, wait, no, this should be 1, 0. Apologies. No, that's also true, false. This should be 0, 1. And then here we get the zero vector. So likewise, we find that F takes us between these two eigenspaces. And so E and F take us between these two eigenspaces. And of course, by definition, H preserves them because we basically took a decomposition of our space according to the H eigenspaces. I mean, mind you, I didn't even have to do the computation, right? Because we're looking at the sort of natural representation. You know, we can read off the eigenvalues from H itself. It's a diagonal matrix. Okay, but I want to highlight this example because of its similarity to the next example. There's also, so of course for these matrix Lie groups, right? Any sort of subalgebra of GLN. Of course, we have this very natural Lie algebra representation of it just acting on Cn in this way. But there's one other very natural Lie algebra representation, and that is to have a Lie algebra act on itself through what's called the adjoint map. I should write little a. So this is going to send an element in Lie algebra to, well, really, I should write this as, I mean, we call it add x, but it's also just the map where we put a Lie algebra element in the first bracket. And now, now if we go back to our Lie bracket computations, right? Maybe I can even copy paste. I don't know why I bothered doing that. It's such a small thing. I could have just rewritten them. But now, right, we know that, so EFH, those are our basis elements here, but we know that EFH are, I mean, they're also basis elements here, so it's enough to determine how these things act. So we have then three-dimensional representation. So well, let's first again look at the eigenspaces of H under this representation, right? I didn't set that many alarms. I only set one alarm yesterday. I don't know what's going on. So we could take H, bracket H. We always know the Lie bracket's going to be 0, right? Actually, let me explain this a little bit better. So we've got our map from SL2 into GL of SL2. And we're going to look at, we send each of these things to this linear transformation. So let's look at the linear transformation H dash, right? So the linear transformation H dash, if we look at each of these 0 vectors, we see that H is a 0 eigenvector for this, right? Because H acting on H will be 0. Does this mean, I suppose this doesn't mean, oh, should this have been a -2 here? I think I made a mistake. That should have been a -2. Yep. So, here we can see that H is actually a 0 eigenvector, And we know that this thing is a linear transformation on a three-dimensional vector space, because SL2 is three-dimensional. And actually, we can see from these computations, we can see its two other eigenvectors. So we know that E, F, and H must be all of its eigenvectors, and we know its eigenvalues. So we can draw another picture, similarly, of V0, V2, and V minus 2, where, of course, H acts essentially by definition on each of these spaces. And we can work out exactly what the we can work out how E and F work. So, and I mean, we might already expect, maybe from last time, maybe there's a pattern here, maybe E does this. So we could just literally do these computations and work it out, right? But I'm going to write this in a slightly fancier way because I have in mind where we're going. If we have, so the goal is to take E and apply that to some thing in the -2 eigenspace, and then see if that then is in the H0 eigenspace. So we can test that by taking H, the Lie bracket of H, with the Lie bracket of E, with something in the -2 eigenspace. And again, because I know, I mean, there's an easier way to work this out, because we already know that that thing in the -2 eigenspace is F. And we already know that EF, its bracket is H, and that this will be 0. But because we want to have a mind towards how we're going to generalize this idea, I want to work this out in another way. And one way to do that is to use the Jacobi identity. So let's see if I permute things in the correct way. So I think this should be the same as, no, that can't possibly be V. Wait, no, it has to be V. What am I doing? I might have to review my Fulton-Harris. Maybe I don't even want to write this. I think perhaps what I wanted to do was to maybe write it as rho H, viewing rho as the Lie algebra representation of rho E of V. And then use the fact I have a Lie algebra homomorphism. I think that's what we need to do. But unfortunately, I have to go. As I mentioned, today would be a very short office hour. We'll continue this and possibly talking about natural transformations and atalmorphisms, well, tomorrow, I suppose. So, go prove some theorems.